Hi there, welcome to the lesson on probability distributions. This is a key topic in our course and also sometimes considered a challenging one, so please think carefully as you work through this video. Alright, let's begin with a very big idea. This will be a recap of something we looked at in class. First of all, we have discrete data, which is data that is either counted or, for example, we have the number of cars in a car park. You can count that, one car, two cars, three cars, and so on. Or it is data that only takes on specific values. For example, shoe size. Shoe sizes are given in values such as 7, 7.5, 8, 9, that kind of thing. Or in centimeters in Europe, 30 centimeters, 33, and so on. That is in opposition to continuous data, which can be measured. For example, height, weight, and time. All data that can be measured means that any single data point can take on any value in a large range of numbers. For example, your weight can be given as a decimal to 2 decimals, 3 decimals, 4 decimals, unlimited. As you can get as detailed as you want. So that is continuous data. Okay, we looked at the coffee shop example. So at a coffee shop, there are 4 percolators or coffee making machines. Let's allow the variable b to represent the number of percolators that breaks in one day. Is this discrete or continuous? Well, we talked about that. This is discrete because 1 percolator can break, or 0, or 2, or 3, or all 4. So it's discrete because we can count the number that can break, and it can only take on those specific values of 0 breaking, 1 breaking, 2 breaking, 3 breaking, and 4 breaking. So the values it can take are those values. So our variable b can be assigned this set of possible values. Again, this represents how many of the coffee machines will break. In contrast to that, we had the example of a bag of coffee beans, and that bag can weigh between 0.98 and 1.03 kilograms. So it's put together in some factory, but as the factory pumps out that bag of coffee beans, it's not perfectly accurate, and the weight can fluctuate a little bit. It can take on any weight between there, depending, of course, on how many beans there are and how much each one weighs and all that. So that's continuous data. So W, the weight of the coffee bag, is continuous. And it can take on any value between 0.98 and 1.03. So to show that full range of possible values rather than just these discrete values, we use the greater than, less than symbols to show that W, the weight, can be between greater than that, less than that. So it means any value between those. Okay, let's look a little further. We also had coffee machines there. So we talked about this being called a discrete random variable because, again, it's discrete data. And that variable is random because it is kind of random how many machines will break in a day. We don't know. We can't predict that. Okay, we created a, you can create a probability distribution table for that. We have the number of percolators here that breaks, and then the probability of each one here. So for example, the probability of 0 breaking is 0.6, probability of 1 breaking, 0.3, and so on. This is called a distribution table. And for example, the probability of 2 breaking is 0.06. So you can always grab one probability from this table of all possibilities. And we also can represent the probability distribution as a bar graph where you show, again, here are your values, all the possible discrete values, 0 breaking, 1, 2, 3, 4 breaking. Of course, we cannot have 5 breaking, so we have nothing there. But it shows on the y-axis here, or the dependent axis, we have the probability. So 0.6 for that one, 1 breaking is 0.3, we can see here, and so on. Okay, with that, let's talk about probability distribution in some more detail. And we have this, to summarize, kind of, we have this. So the general table for probability distribution looks like this, right? We have the number of something and then the probability of each of the things here. So again, our specific example here, rather than using these symbols, we know what those probabilities are, so I just wrote them in here. 2 key points here is, hold on, let me point that out. One key point is that these values must add up to 1. So, as you know, these show all the possible outcomes, right? There can be 0 breaking, 4 breaking, or anything in between. So that shows all the possibilities that can happen in this coffee shop. Therefore, if you add up all those probabilities, it must add up to 1 or 100%, because this covers all the options possible. That's something really key to know there. And the second thing you should know is that this thing here. What this means is that every probability value in this table, so each of these values must be between 0 and 1. And that makes sense as well because a single event must have a probability between 0 and 1. All right, on the bottom here we have a discrete probability distribution function. We also talked about that during our investigation in class. But basically you can take the probability data that we have in the table and we can express it as a function. So here we say the probability, each of these single probabilities can be expressed in these two functions. So this is a piecewise function. And basically we have anything from 2 to 5. So this one here, 2 to 5, yeah, it occurs with this probability. But this was for not this example, this was for a different one. Basically we're creating a function to represent all the possible probabilities. That function is often called a PDF, which means a probability distribution function. Okay, so let's begin with our first problem here. Let's solve this one. We have to show that this function defines a discrete probability distribution. So in other words, we have this function, we're going to put some values in it, we're going to create the results of putting those values in, and hopefully that all those results actually represent a probability distribution. So let's see if we can begin by constructing a table for this. So look at here that t can be any value from 3 to 7, right? So anything equal to 3 or greater and up to 7, including 7. So in other words, t can take on the values 3, 4, 5, 6, and 7. So try plugging each of those t values in here and create a table like we had before, like this kind of table using 3, 4, 5, 6, 7. Let's see what your table looks like. Okay, so here's what the table should kind of look like when you fill it in. Let's ask you for this third value. I'm just curious, what's your third one here? Let's see if we can get the correct answer. Okay, so here's the full table, and the third value was when t is 5, we get the function produces 3/15, and that works by putting a 5 in here. 5 minus 2, 3/15. So when we put t value of 5 in there, we get a result of 3/15, and that is the result of the function that shows here. So this is now just a table of values, but does this represent a probability distribution? So again, remember, what do these all have to add up to? So double check, does this represent a probability distribution? What do you think? Okay, so what we do is we can add up all these probabilities, and notice we're doing that work here, 1 plus 2 plus 3 plus 5, add those up over 15, and you get 1. When you add all these, in other words, when you add all these fractions up, it gives you a total of 1. And that, therefore, that means that this function that we had on this particular domain creates a probability distribution for a discrete. So it works. If this does not equal 1, you would say, well, no, that function does not create a probability distribution because all the possibilities must not be listed. But since they all add up to 1 here, it means all the possibilities, 3 through 7, are listed and nothing else is possible. All right, and to create a bar chart for that, basically you take the values now that you have them, you put your possibilities here, your probabilities on this axis, and you make a bar chart for that. Okay, next question. Let's say you have a fair cubical die, so right here, and a fair tetrahedral die. So, and now you roll these two dice together. The discrete random variable S is defined as the sum of the numbers on the two dice. So again, we ran this simulation in class already. We got some of these things done already. Let's take a look. So if you're rolling those two dice, you can create a sample space diagram. Here's a 4-sided die. Here's a 6-sided die. And here we have all the possible sums. For example, if you roll a 1 and a 1, the sum is 2. Or if you roll a 3 and a 4, the sum is 7. So this is all the possible sums when you roll these dice. And then it says, show that as a table of values, or here's a table of values, right? Here's all the possible rolls, the sum of 2, and the highest sum is 10. So here's all the possible sums, and here's the probability of each one. So we've created a probability distribution table, and we know these values. For example, a 2 can only be rolled one way out of these 24 different options, so 1 out of 24, or a 3 can be rolled 2 different ways here, so a 3 can occur 2 times out of 24, and that's how we get the whole table. All those values, again, should add up to 1. Now, it says then make a bar chart, so here's a bar chart for the same information. Here's the rolls of 2 through 10, and here's the probability of each one. And finally, you can also represent that as a piecewise function, and just recapping what we've done already. But here's the function. This function is piecewise in 3 parts because between, let's see, when s is 2 to 4, 1, 2, 3, these values here, then you can see the probability is rising by 1. It's 1 here, 2, 3. So the top of the fraction is always the sum number minus 1, right? So 2 minus 1 gives us the 1 here, or 3 minus 2 here. Sorry, 3 minus 1 gives us 2. So this function can be used to create these 3 values. So only when s is that. And then we have the middle values of when you roll a sum of 5, 6, or 7. Those all have the same probability. So that's what we have here. We have a probability of 1/6 when the s value, the sum is 5 to 7. And the final function shows us these upper ones here. When we have a sum of 8, 9, 10, the function for that can be this. Basically, when s is 8, this is 3, therefore we have to have 11 minus 8 to create that 3. And let's see if that works for the next one. 11 minus 9 gives us a 2. So this function works for the last 3, and we see it shows it here. It only works when s is 8, 9, or 10, which is those 3. Make sure you take a close look at that if you're still struggling with creating that. Okay, now let's see if we can answer these questions here. These questions here are based on the probability distribution we just created for these die rolls. So what's the probability of the sum being greater than 2? Okay, for the sum to be greater than 2, if you look at our whole distribution table, it has all the possibilities there. The only time the sum is greater than 2 for all these choices here, right? Here the sum is 3, 4, 5. So everything, all these ones here are a sum greater than 2. So rather than adding up all those probabilities, we can just say 1 because the total is 1. 1 minus the only time it's not greater than 2, which is this. So 1 minus the 1/24 gives us the remainder, which is all those. And all those are times when this roll is greater than 3, or 2, sorry. So that's our answer there. Now let's look at the next one. Next question says probability that s is at most 6. Think about what that means. The sum is at most 6. Okay, for this one here, that means at most 6. That means we're looking for a sum of 6 or lower because it is at most 6. It can't be something higher. So we're looking for sums of 6 or less, right? So sums of less than or equal to 6. So basically it means all these ones here. So if you add up all those values, that plus that plus that plus that, all those, here they use different denominators because they simplified some of these fractions. But basically, if you combine those, you should get this fraction here. Okay, and last one. This one is a difficult question, not easy. So you have probability the sum is less than or equal to 6, given that it is greater than 2. So notice it's combining these two first parts we did, but into the dependent formula. And if you remember how dependence works, you should be able to calculate that. Try that now. Okay, so what we have here is dependence formula tells us when you have something dependent on something else, you do the intersection of those two things on top. And on the bottom, so here, that symbol means you're going to do intersection of those two things. And on the bottom, you're always going to put this thing here. If you remember the lesson we had on dependence, basically how it works is that you say, we're looking for these things out of this group. So now instead of looking at all the possibilities, we're looking at only these possibilities. That's why we're doing this out of this here. So this stuff taken out of only this group. So the intersection of those of less than 6 and greater than 2. So less than 6 and greater than 2 is basically these ones here. 1, 2, 3, 4. Those 4. Those are greater than 2 but less than or equal to 6. So that's the sum of those out of the greater than 2 group, and we get this answer here. Definitely study this one carefully. It's a tough concept for many students. Another way to look at this one is visually. When you have here is your blue category, which is that sum is greater than 2. So all those are sums greater than 2. So that's going to be our bottom number. If you add those up, those are 23 out of 24. And here, these ones are the less than 6, but still greater than 2. So those ones go on top here, and the blue goes on the bottom here. All right, there's a second video for you on this lesson. Make sure to watch that now, and then we'll do all the homework assignment in class together. See you soon.